Hello, I am Marzia Polito, and today I will talk about how we at AWS help non-machine learning experts to build high-quality computer vision models using only a few examples. Computer vision and the ability to build models to classify and recognize objects and scenes has advanced tremendously in the past few decades. With the help of deep neural nets and building on solid foundations of understanding visual features coarse and fine, computer scientists have been able to significantly advance the state of the art. Large annotated datasets like ImageNet or COCO have played a critical role in feeding the data-hungry neural nets and in providing reliable test set and benchmarks. The volume of computer vision publications has grown immensely, and the amount of analyzable data has also grown a lot. Think all streamed content, all shared images on social media, all monitoring images in industrial and personal settings. But labeling remains very expensive and hard, and it does not scale as well. At the same time, the needs have become more and more sophisticated. So it's time to figure out how to make all these advances more available to all scientists, professionals, business users who rely on visual data every day as a critical component of their personal and professional lives. These are biologists, psychologists, sports professionals, media industry people, archaeologists, architects, agronomists, or just folks like you or me sitting with our laptops and trying to organize our family photos. And as you will see, our data, our labels, and sometimes even the formulation of the problems don't always look like academic data sets. At AWS, we are fortunate to get inspired by our customers and have access to real problems so that we can let our research be inspired by them and often solve them. In 2019, AWS launched Rekognition custom labels, allowing you to identify the objects and scenes in images that are specific to your business needs. Developing a custom model to analyze images is a significant undertaking that requires time, expertise, and resources, often taking months to complete. Additionally, it often requires thousands or tens of thousands of hand-labeled images to provide the model with enough data to make accurate decisions. Generating this data can take months to gather and require large teams of labelers to prepare it for use in machine learning. With Amazon Rekognition custom labels, we take care of the heavy lifting for you. Hao Yang from the custom labels team will show us how.
In this demo, we'll showcase the whole workflow of training a single object detector on everyone's favorite food, pizzas, with just a small amount of data. To use custom labels, you will need to first create a project, which can be easily done by typing the desired project name and hit Create Project. The more interesting and important part is in creating datasets. After you enter your dataset name, you have multiple options. You can import from Amazon S3 buckets, copy existing datasets, or import the annotating dataset from SageMaker Ground Truth. In this demo, we'll focus on the more streamlined way of uploading and annotating images using Custom Labels console by selecting the Upload Image from your computer option. After the dataset is created, we can use the Add Images button to either directly upload or more easily just drag and drop multiple images as shown here. We have successfully added 21 pizza images to the dataset. Now, we will annotate the dataset with bounding boxes to set up a detection task. We first need to add labels to the dataset. Since we only have one class, we just need to type Peter, click Add Labels, and save. For classification, the annotation process is just assigning labels to each image. For detection, we will need to draw bounding boxes. By selecting the target image and click Draw Bounding Box, we can navigate to go to the annotation tool. For users without much experiences in this task, we provide tips to help them. When using the tool, we first need to select one label. Here, Peter is pre-selected as we just have one class. Then, we draw a type bounding box around the object of that label. Once we have done that for all the objects and labels in the image, we click Done to go back to the dataset page. Please note that the current annotation is not safe until we click Save Changes. Then we can see the annotated image in Label section on the left. After we annotate a desirable amount of training images, we can start to train a model. Our custom labels algorithm will choose the suitable method and hyperparameters based on dataset properties such as annotation type, number of images per class, etc., without the need of any user input. However, there's a saying that your model is only as good as your test set. So we need to first create a test set. There are several ways to do that. We can use a separate test set by choosing an existing one or creating a new one. Or we can split the training set by 80-20 for quick turnaround. Once we specify the test set, we just need to click Train button and the system will take care of the training and evaluation. Once the training job is finished, we will generate metrics and the evaluation reports on the provided or splitted test set. For metrics, we use F1 score, precision, recall. Specifically, we assume the initial thresholds based on the maximum F1 score we can achieve on the precision recall curve. This threshold can be changed based on the user's specific requirements of precision or recall. In the View Test Result page, we also provide detailed false positive and false negative analysis of each image in order to dive deeper into the error patterns and provide more data points to improve the model. To use the trained model in production, Custom Labels provide fully managed hosting service. Currently, we support both AWS CLI command and Python API. The inference process is as simple as starting a model with the provided command line snippet. Then you can easily inference on images in the S3 buckets.
Custom Labels is used by a large variety of customers operating in multiple domains. Customers in the industrial sector need to recognize products and machine parts or detect damage. Retail may need to do inventory management. Healthcare and accountancy may need to classify documents. Entertainment and media may need to classify animated character or icons, logos, symbols. Botanists or zoologists may need to analyze plants or animals and their movement. For some sectors, specific needs grant the spin-off of a dedicated product. Amazon Lookout for Vision is a machine learning service that spots defects and anomalies in visual representations. With Amazon Lookout for Vision, manufacturing companies can increase quality and reduce operational costs by quickly identifying differences in images and objects at scale. For example, Amazon Lookout for Vision can be used to identify missing components in products, damage to vehicles or structures, irregularities in product lines, minuscule defects in silicon wafers, and other similar problems. Lookout for Vision also offers the customer the opportunity to review the output of our system and confirm or question it to the benefit of the next iteration of the model. This functionality will come to Custom Labels soon. But what went into these products? Let's look at the challenges. Label data is scarce and expensive to collect. And frankly, the AI promise is making people wonder, why do we need so many images of the same thing? I can recognize things that I have seen just a few times, to the point of taking a risk on eating mushrooms. I can group objects that I have never seen before and I don't know what they are, but when I find out what one of them is, for example, a rose, I can transfer the knowledge to all others. I can produce a mental image of what something would be like when rotated, scaled, partially occluded, or just not the main object in the image, like Coke in the presence of pizza. If I have seen enough similar tasks, I can solve a new one real quick. After all, this is not the first time I've seen species where male has headgear and female doesn't. I can also select which experts to call in if I see something I'm unsure about. I'm sure my brother-in-law, for example, would recognize this old rusty car. Why can't machines do that? Labels are also a very wide and varied universe. It's typically not cats versus dogs. Its nuances is very special things like golden or Monty kiwi fruits. Its absence of objects like missing components in a circuit board. It's things like assistive sport refereeing with explicit or implicit hierarchies like potential yellow cards, fouls, or shirt pulls. Its behaviors already evident from one image like punching cats. It's unthinkable and also not efficient to have models ready and available for all these specific use cases. A significant level of customization is typically needed for each case. Some visual questions are quite involved. Can you count these penguins for me? Can you tell me how many pieces of Legos of each shape and color do I need to build this object? Can you tell me if I should get on the field and replace these electric transformers before it sets the grass below on fire? And most importantly, where exactly is the panda? Wait, I meant, where's the umbrella? Actually, I need both. All of these complex problems are often solved in multiple stages, often refined after the first definition, all different from each other. Summarizing, we have established that in real life, visual questions can be complex and can evolve in time. They come typically with a few labeled data, as it is expensive or time-consuming to collect them. And they cover a long tail of labels that we have possibly never seen before. These settings force us to use a different set of techniques. Let's talk about some of them. So what's the problem of having just a few images? Our neural nets should be powerful enough to recognize the objects anyway, right? Unfortunately, they have a tendency to overfit to the little they see and forget to classify an orange rose as rose as there were no orange roses seen before. This is interesting, as when we see this example, we naturally feel like saying that the orange rose is a rose, despite the previous unseen color. What prevents us from being fooled by the color? The point is that we do have additional knowledge, which we are able to transfer. Suppose we need to separate two classes of dots, but for just few of them we have labels, yellow and blue, in this image. Well, the point is that maybe we already have learned to separate green from red or black from white. Still, with other few shot situations. So yellow from blue won't seem that hard anymore. The idea is that we have learned how to learn, as we have seen many annotated data points before, with other similar yet not overlapping few shot tasks. Typically, we don't just look at data points for this task in isolation, but we map our knowledge in some high-level abstraction implicitly based on transferable visual features, like color, here represented by a vector space embedding. We then use our previous learning experience as a template, here represented by a learner, to solve our task at hand. Meta-learning is appropriate when one has access to only a few annotated examples for the current task, but has or had access to a large annotated set, not necessarily containing the same classes, but similar ones. Let's now move to see some of our group's contribution in this area. Roses are not fully new to us. They are flowers, after all. We already know where to map them in our knowledge repository, even if we haven't yet learned their specific characteristics. In computer vision, this is represented by embedding all flowers to a common vector space, where we've already identified what dimensions are the most useful to distinguish flowers. For example, gerania can also be orange and of other colors. So why should orange be a deal breaker for roses? Embeddings are based on visual features. In this 2019 CVPR paper, we moved away from the traditional representation of classes as Euclidean average of the samples in the class, and we allow class models to live in a different high-dimensional space, learning those parameters at the same time, allowing for more complex and extendable class definitions. Once we have embedded examples in a high-dimensional vector space, we need a way to separate classes. As shown in the previous slides, traditionally nearest neighbors-based techniques were used. In this CVPR paper from our group, we proved that using regularized linear models as learner is a better choice, as they allow significantly higher embedding dimensions with reduced overfitting. Customers may not have large amount of labeled data, and we may not be able to help either, as our own labeled data set may be too generic, but they may have a lot of unlabeled data belonging to their own task. This is typically the case when annotation is expensive. In meta-learning and in many other learning situations, one learns a function that maps the input to the output and can extend later to different new input. In transductive learning, the focus is to just learn the class assignment for the test set, which must be available all at the same time. In a 2020 ICLR paper, our group proposed a simple transductive fine-tuning algorithm as baseline for few-shot. We add to the usual log loss function a term that regularizes by seeking a low Shannon entropy, hence picked posterior probability. This guarantees that the endpoint is a good distribution. So the first term uses labeled data, the second all unlabeled one. Semi-supervised learning is also a common technique for few-shot learning. It aims to learn a model using a few labeled data and a larger number of unlabeled data. Unlike transductive learning, we do not assume that all the instances to be labeled are available upfront, and we aim for generalization to future instances. Deep learning semi-supervised methods typically aim to iteratively increase the number of labeled data points by using currently labeled data as teacher for a student model, and then select the most confident students to be teachers at the next iteration. Our 2021 CVPR paper, EMAN, improves the performance of the student-teacher models for self and semi-supervised learning. Another aspect that is fundamental to our customer is control at the level of individual data points. It is important to understand what is the effect of individual data points on the network trained. It is important to be able to forget individual data points because we lost the right to use the data, because it's unfair, or just simply wrong. And it's important to be able to do it quickly and without retraining the whole model, which we may not even be able to do due to constantly evolving data availability. This gives us more flexibility, especially when we have few labeled data. Our group addressed these issues in two CVPR 2021 papers, where we proved that models obtained as linear Taylor expansion around the pre-trained model are, under realistic settings, as good as fully fine-tuned ones, and satisfy the desirable properties I just mentioned. Most of the methods I describe rely on the assumption that there is a unique embedding. The lens itself well to be adapted to solve any few-shot task at hand. But we have to admit that the universal knowledge doesn't exist, and we'd all expert if we could. Even if the expertise is not exactly in that field but in a similar one, I'd rather ask my dentist about an eye problem than my plumber, as they share a medical background. But how do we learn and represent this task similarity? In this ICCV 2019 paper, we provide a fixed dimensional embedding of the task that requires no understanding of the class label semantics. We demonstrate that this embedding is capable of predicting task similarities that match our intuition about semantic and taxonomic relations between different visual tasks. So, are we now ready to build real-world models on behalf of non-machine learning experts? Let's check. We outlined different learning paradigms for few-shot, the most common real-world situation, under different constraints and other forms of information beside the few labeled data points for the task at hand, such as large amounts of annotated data, or a large amount of data labeled in other similar categories. We explored the robustness, interpretability, and simplicity of linear learners and convex optimization. We established the need of multiple expert models in different domains. We found ways to determine which ones of those are the most promising to start from in order to solve our task. In conclusion, we presented two of our products that support non-machine learning experts in building high-quality models with their few labeled data. We highlighted some characteristics of these real-world problems. We delved into few-shot learning, explained some techniques, and highlighted some of our research contributions. We explained how these aspects can be joined together as ingredients in a recipe to build systems like custom labels and lookout for vision. If you want to learn more about machine learning with AWS, you can check out this URL, which will give you a lot of resources to enhance your knowledge. Thank you.